Please just open your mic and just let me know if you have any questions. So now we need to solve the problem one more time. So we have this iris data set. So we need to build a perceptron, and this perceptron will have two inputs, right? We calculate here summation. We have two inputs, x1 and x2, petal length and petal width. You can just select. Please remember to standardize. So this one will be omega 1, this one will be omega 2, and we will have here the bias, correct? So it's +1, and we have here bias. So we will have a decision line. So this decision line will be omega 1, x1 plus omega 2, x2 plus b equals 0. So this is our decision line. You will apply some activation function here, right? I mean, if you will use a perceptron anyway, you can just, if you want to use the program which we did last time in details, it's fine. If you want to use something from sklearn, it's okay. So we'll have here some activation function. We will use hard-lim activation function, and we will calculate the output one. So it's binary classification problem. So we will select the first 100 points because the data set, in fact, it consists of 3 blocks. We have x1, we have x2, we have x3, we have x4, and we have target. So the first 50 points are related to one class. It's called Setosa, for example. And after that, another 50 for Versicolor, and the last for the third class. So in fact, we have, so when we selected here, I just selected the first 2 sections. I selected the first 2 sections. But I didn't shuffle it. In fact, do you remember? When I trained my model, I didn't shuffle. I just used the first 2 blocks for training my perceptron. So just please, I mean, go to the code and try to make it in much better way. So we need to, after getting your x and y, so I need to get x and y. It's from datasets.iris. You need to shuffle it, but if you will use train test split, if you will use this function, you don't need to shuffle because it will be shuffled automatically. And after that, you need to divide this one into one part for training, right? One part for training and one part for testing. It could be this one, for example, 30%, and this one it could be 70%. When you train your model, we need to get for training, we need to get prediction error for training. We can call it E training, for example, E training. And for testing also, we will have error for testing. So we need to get those 2 values. We need to get those 2 values. So just feel free to, if you have any question, please just ask me, please. Today, we will make it easy because, I mean, practically, I mean, we can, of course, write our own code as we did last time. It was easy to put this model in, I mean, to implement this model from scratch and to train it. But this time we will use sklearn. We need to be more practical, so we will use sklearn. sklearn, we have lots of models, so we will select a linear regression, and a perceptron, it's one of those linear regression models. So we need to import, I mean, from sklearn.linear models, we need to import logistic a perceptron, right? We need to import a perceptron. So we will train it on the training data set, testing it on the test data set, and plot the decision line. I mean, for the decision line, this is the decision line, in fact. This one, it's the decision line. So if I have my data points like this one, I have my data points like this one. So we have here x1, we have here x2, correct? So just generate a range of the points covering x1 using line space, for example, or so I just used x. I generated a values for x1. It could be, for example, some numbers. So it's -1, -0.9, -0.8, until +1. So I selected those data points for x1. I will just substitute it into this equation. I have x1, so I need to find a value for x2. So how can we get x2? So x2 will be negative omega 1 x1 plus b divided by omega 2. So now we have x1 and x2, and just plot x1 and x2. So now when you plot x1 and x2, you will generate this green line, which is a decision line. So if I have one class here, it's a red class and blue class, for example. We have here this blue class here. I have some points. This is the blue points. And red class, so it's some points here. So in this case, we can plot a decision line which will be look like this one. So we just did that today. I mean, and of course, training. We used as a training. You will use a training data set to find good values for omega 1, omega 2, and b. We started from random values, and after that, you will just try to update those values in a way to minimize the prediction error. So the most important now for us is to find the prediction error for the training and the prediction error for testing. This is very important. So please just open your mic, and I know some people are writing, but yes. Okay. So is it working, Michelle? Is it working with you? This model.predict? Yeah, of course. Predict, not y-test. It should be x-test, because when we are predicting, we need to have some features, and from those features, we need to predict which class. So thanks, Michelle. So Michelle has solved it for you, Mohammed. It would be great also if you can plot, the learning curve in training and testing. When we also, this is the easiest way for plotting. This is the easiest way for plotting. This is the easiest way for plotting the decision line. But if you want to plot the decision line in different way, so how can we get? So I want, if you want to plot the decision line in different way, I mean the decision boundaries. So it's the same also. We have two features. So we have x1, we have x2, right? And of course x1 we have here x1 minimum, or I mean no problem. I will just, so I have all those values in fact. So the idea here is to generate a grid. So we will try to generate a grid, right? We will generate a grid. First, I will generate values for x1 with some step, for example, or so. I will get those values for x1, and for x2 also we will get some values here. You can do it by line space, for example, or in b.arrange. So I will show you an example. This value here, it's imagine this value here, it's -2. This one it's +2, correct? Imagine this value for x2 here, it's -3. This one here, it's -5, for example. So we'll generate all values. I mean, we will generate some values here, and we will generate this grid. So first, I can just say, okay, x1 equal, I mean, all values. I mean, so it could be, for example, I mean, it's line space, for example. So we have this NP line space. Line space, it's from -2 to +2 using, I mean, you can generate, for example, 100 points or 10 points or whatever. So this one, it's x1. You will get x2 in the same way. You have x1 and x2. You will use this mesh grid. So I need to generate a grid. So I will call it x1, x grid 2 equal np dot mesh grid of all points x1 and x2. So now we generated a grid in fact. So now we have all those points here, right? We have all those points. So at each point, I will apply my prediction model. So at each point of those, I will find the prediction in which class. Is it the positive class or is it the negative class? We know all data points which are, because I have this originally, I have this line. So originally we have this line here. We have this decision line, right? All points which are above it, we will call it positive class, right? So all points which are located above, we call it positive, and below it, it's negative, right? So now we will be working with each point of those, and for at each point here, we will find. I will apply the prediction. So it's called the model dot predict, and the input here will be this value, the x1 value. I will call it x grid 1 and x grid 2, for example, x grid 1 and x grid 2. So I will send all those values, and I will find in which class they are belonging to. Is it does it belong to positive class or negative class? So I repeat this process. We will repeat this process for all points, right? We will repeat this one for all points, and finally I can plot it using a 3D plot. So it's much easier also, and it's not a problem. So did you finish running your code? Can you get those two numbers? I want from you the two numbers. Prediction error for training and the prediction error for testing.
I'm not sure if they are correct, but I got, I think they are not, because I got 0.58 for the training and 0% for the testing, which doesn't make sense. No. It's like 60% for training and 100% for testing.
For testing.
Yeah.
Yeah. And did you use so
Maybe we have to
how
wait
much
for
for
others.
training? How much for testing?
Training, it was 0.58, which is 58%, and the other one I got no error. Everything was separated in a good way, like zero error.
Yeah. Okay. Any other numbers from? But it's easy to make those. It's easy to make those changes, and yeah.
I have a question that you are saying that we need prediction error on training data as well. While we are training, how can we get an error? Because we are assigning the label itself.
Prediction error. It's just I want to test that performance. So I have target features and predicted features, correct? So just subtract and define the mean square error. So I call it prediction, but it's not. It should not be prediction, right?
Yeah.
But
so I should.
It's the performance of my model, right? It's the performance. So we need to count how many cases my model cannot classify, or how many misclassified cases.
But that should be on testing data only. Why should we do this on training data?
I mean, it's because
error calculation.
Yeah, because maybe my model has a problem, has overfitting a problem. So we need to discover it from those numbers. So if your model is performing very good with the training and very bad with the testing, we can identify that we have overfitting a problem. Right? So how can we identify that the model has overfitting? Right? So overfitting means my model will memorize my training data points, and it will not be able to generalize to my testing data points.
My question is, why is there a need for error calculation on the training data? We can just get it on. We can train the model on the training data and get the error from the testing data. Isn't this the right approach?
Yeah. So you can plot it. You can have the graph, right? Learning graph, and you can see those numbers from the graph, or you can just print it on the screen. Can you share your screen? Did you get it by different way, in another way?
Okay, I can share my screen.
Yes. Just share your screen with me and show it to me, please.
So I'm not authorized actually to share my screen. You have to give me information.
Okay, who is talking, please, so I can. What's your name, please? Hussein?
Muhammad Saad.
Muhammad. Okay, Muhammad. I will. Not start the video, but I want you to share, but I cannot find it here. It looks like I must make you a host.
Okay, no worries. I have to test. I have to calculate the error on the prediction data on the training data yet. So I was just willing to ask that why is there a need to test it on training data? So yeah, I should test it and see the performance. Yeah.
Yes. We need to test it because I mean we need to know how good the model will perform, right? Or is performing on the testing and the training. Because if your model has very good performance on the training, maybe it has good performance or bad performance. So we need to know, right? If it has bad performance, it means it's underfitting a problem. And when it's underfitting a problem, it means maybe my data set is not enough. I need to get more data. And maybe my model is too simple to my data set, and he cannot learn my data set. He cannot train my data set. So in this case, I need to make my model more complex. And if the system, if this error is too small, maybe my model is more complex for my data set because it will memorize. I mean the capacity of the model. You remember last 2 weeks we talked about something called model capacity. So when the model is really complex and the system, I mean the data set it's a simple, so the model will tend to memorize your data points. It will not be able to generalize, but it will try to memorize it, and it cannot generalize for testing data set. So I need to know, I need to identify if the model has overfitting or underfitting a problem, and we can identify this from those 2 numbers. So those 2 numbers are very important for us.
All right. Thank you.
Because if your model has underfitting a problem, in this case, I need to change, I mean, model hyperparameter. I need to make my model more complex. Maybe we need to generate more data points I mean, and if the model is too complex, we need to make it simple. We need to put some, I mean, we need to know how can we restrict model capacity, for example, right? So maybe you can use this early stopping, for example. Maybe we can put some restrictions on values of wheel values which a model can select or can reach, so the model can train. I mean, can train and not memorize the data points. So this is very, very important. So all people, we are in the same page. Everyone has got those numbers. Bidder, Ravi, Abdurrahman, Amir, Andreas. Okay, so in this case, should we go to the next slide? Okay, so I will just and I just explained it to you. I mean, plotting should be fine also. So now we will go back to the PowerPoint and okay. So now we will go back to this problem. I mean, plotting. I mean, so I just mentioned that it's very important to evaluate the trained model performance on unseen data. So it's very important to divide your data into a training and a testing sets. We need to have a set for training and a set for testing. And as I told you, this function, in fact, it shuffles the data, in fact. So don't need to worry about shuffling the data set, because this function will internally shuffle your data before dividing it. Because shuffling the data set is very important. Why it's important? It's important because I need all data points to be all classes to be represented in my data set. And hold out validation, we will keep this one away. I mean, we will have a training set and a testing set. We will keep the test set away for testing our model. So I have my data set. We will use this train test split, and we will divide it into one section for training and one section for testing, right? If it is hold out validation, if it is I mean cross validation, of course, it's a different story, and we use cross validation when my data set is really very small. You need to be careful about stratify. This is very important, especially when your data set is small. You need to have a balance. You need to have balanced data set. If it's not balanced, your model will be just biased, right? The second part here, it's about linear models for multi. Yes, we have some questions. Yes. Yes, you have this one in the code. I mean, you have the link already in the slides, Muhammad. So you can just get Ahmed. Okay, yes, Ahmed. I mean, the code is you have a line already. I mean, you have the link for the GitHub. Yes, I can share it with you. Yes.
Yeah. I have the link. No, I'm there. No, I'm just asking about why did he get 0 when he, in the error for training. I just want to see which mistake did I made while coding. But he did share it with me, so everything is okay now.
Yeah. I mean, and also plot. But we later on we will plot the confusion matrix. It's very important to see the confusion matrix because it will help us to understand how the test set is look like, and maybe just because we used 100 iterations, right? Try to reduce it, for example, 10, for example, 20, and you see maybe it's a trend a lot. It has been trend a lot, and mhm. Yes. So we will talk about linear models for multi-class classifications. Linear models for multi-class. We have been working. I mean, if we are using a perceptron or adaptive linear unit, we are doing it for binary classification. But is it possible to extend it to multi-class classification? Because in this iris data set, we have 3 classes, in fact, right? So how can we do it? So in fact, it's a very simple trick. We did the perceptron for 2 classes. So this trick, in fact, it's so we can do it only for 2 classes. So perceptron or adaptive linear unit, we can use it only for 2 classes. We can do it for only 2 classes, but if you want to do it for multi-class, so we need to use a trick. I mean, this trick, it's called one versus rest. And the one versus rest, in fact, it's a common technique to extend the binary classification algorithm to multi-class classification algorithm. We call it OVR, or one versus the rest. So in fact, in our problem here for this iris, in this iris data set, we have 3 classes. So in fact, we will build a model for each class. We will build a model for each class to classify one class against the rest. So, and they call it one versus rest. So if you want to extend this perceptron for 3 classes, not binary classes, so in this case, I will use the first 150 points. So in this case, we will build one model for each class. So at the end, we will have 3 models, 3 perceptrons. One for classifying each class against the rest. So for example, I mean, in our example here, we have 3 classes. Maybe one is green, one is one blue, one yellow, for example, one green, blue, and red, for example. So we will generate one class for the red to correctly classify the red class against the rest. So they call it one versus rest. And for the green one, we will try to find a model to classify the green one in one class against all the rest of the data. For the blue, we will train a model. We will have one perceptron for classifying the blue one against the rest. So this technique, we call it one versus rest. So in fact, at the end, we will have 3 perceptrons, one perceptron for each class. So in this case, we are expecting 3 decision lines, because one perceptron, we will get a perceptron for each decision line. Do you see this one? So we have here 2 classes. From those 2 classes, we got one decision line. We got this decision line from a perceptron. If you have 3 classes, if you want to extend this one to multi-class classification problem, so in this case, we need to generate 3 decision line, one for each class against the rest, right? So in one versus rest approach, a binary model is learned for each class that tries to separate that class from all of the other classes, resulting in as many binary models as there are classes. So we will get a number of binary models equal to the number of classes which we have. So having one binary classifier per class results in having one vector of coefficient. We will have a vector of coefficient omega and one intercept. We will have a vector of omega and a vector of intercept. So in fact, we should expect, if you want to extend this problem to multi-class classification problem, we should expect a vector of omega, right? And a vector of intercept. And in sklearn, in fact, it provides, we have lots of data sets. I mean, you can generate a customized data set. You can just use iris data set, for example, for this problem. But in sklearn, in fact, we have this advantage. We can generate custom data sets. And those custom data sets, we can use it for testing algorithms. So if you are developing, as I mentioned before, if you are developing a new algorithm, you need to test it with a customized data set. You can just customize it. You can just generate as many classes as you want, and you also can control the distribution of data points and so on. So it will give you better control on how the data set will look like. And one of those examples, it's MakeBlobs. MakeBlobs, it generates isotropic Gaussian blobs for clustering. So we can use this function for generating a customized data set for clustering. And I will use it here, in fact, for explaining how can we extend a binary classifier for multi-class classification. So we have here 3 classes. I just generated it. You have 3 classes. We have, it's like Iris data set, right? But we have good separation, and I mean, you can just do, you can control the overlap, right? You can just control, you can generate whatever you want, in fact, using this function. So it has lots of arguments, lots of options. You can use those options to customize the data set which you want to get. So we have here 3 classes. I want to move it here. So we have here 3 classes, right? We have this green class, right? We have this green class. I don't know how can we, if it is possible to write here. Yes. So in fact, we have here, yes. We have 3 classes. We have this green one, right? We have this blue one. I don't know why it's not working with me. So we have this green one here. We have this yellow one, right? We have the blue one, right? And we have the green one. We have 3 classes. We generated those 3 classes from this MakeBlobs function from sklearn. So, and now we need to classify this problem. How can we have 3 classes, right? And it's linearly separable, which means we can find a straight line to divide those classes. So I can find a line here, right? So in fact, in this one versus rest, I need to find, for example, for the green one, I will generate a line like this one. We will draw a line like this one. So this line will be very good. It's one versus the rest. One versus rest. So we need to find this line. So this one will be 1 perceptron. This one will be 1 perceptron. It will be model 1, for example. You can just say it's model 1 or green model. So this one, it's model 1. And also for the blue one, we will generate, we will find a line like this one, correct? So it's 1 versus the rest. So this one will classify, it will classify the blue one as 1 class, and the rest will be another class. So it's 1 versus the rest. And for the red one, it will be the same. We also try to find a line like this one. So it's 1 versus, so this line, in fact, it will classify the red one as class 1 and the rest as class 2, for example. So in this case, we will have model 1 for classifying the green one as maybe class as the green and the rest as something else. We will have here model 2. We will have here model 3. So this one will be model 2. This one will be model 3. So in this case, we will have, in fact, we will have 3 perceptrons. So we have here 2 features. We have 2 input features. So if we need to plot this model, it will be like this one. We will have a model here. It will have 2 inputs, x1 and x2. And this one will be model 1. We will repeat this one more time. So it will connect like this one, model 2. This one will be model 1, model 2. We will have another one also connecting inputs to this model. It will be M3. So in fact, extending it into this multi-class classification problem, it's like generating 1 perceptron for each class. Just generating one perceptron for each class, and they call it 1 versus rest. 1 versus rest. So we generate a straight line or a decision line, which will classify 1 class as 1 class, and the rest will be total. All the rest will be another class. Will be something different. So maybe this one will be 1, the rest will be 0. For the green one will be 1, and the rest will be zeros. So in this case, we can generate 3 models. And if you can see it here, I just did it using a perceptron, in fact, in sklearn, and I got for class 0, I have a decision line, and this is omega 1 and omega 2. We have omega 1 and omega 2 for class 0, and it has B. So in fact, this is for model 1. This one, it says a decision line for model 2. This one will be the decision line for model 3. So in fact, we got 3 decision lines, and each line has been generated by 1 perceptron. So in this case, we can extend. Now we can extend this perceptron or adaptive linear unit for multi-class classification problem. So I recommend you to just try to generate different data points, try to make it more complex, try to generate to find some overlap between data points, and try to make it more complex and play with it. So this approach, we call it one versus rest approach. One versus rest approach, and this is the one approach which we can use for using a perceptron or adaptive linear unit for solving this multi-class classification problem. Multi-class classification problem, it's not binary, but we have many classes. So we have class 0, class 1, class 2, and so on. So it's multi-class classification problem. So you are not going to the bank to get loan. They will not say yes and no. It will not binary problem. No, but there will be a third option. Maybe they will study your case more, for example. So in this case, we can call it multi-class classification problem. Yes. So can you see my screen? So now we will go back to the code, and we will try to implement. We need to implement it. So you have this code. It's called the MakePlops logistic regression. Try to go to this file, MakePlops logistic regression, and open it. So first we need to. It's just from the data sets. I mean, last time we got from sklearn data sets, we got iris. Now we will make plops. So using this MakePlops, it will generate a customized data set. So how to generate it? So just, I mean, it's xy equal MakePlops. I mean, there are lots of options here you can change, in fact. So here there are many things here, in fact, which you can generate. So this random state equal 42, it's just as a random state. But there are, I mean, if you search for MakePlops, you will find lots of options. So in fact, you can generate different, and you can control how the data set will look like, how many classes. I mean, by default, I'm just using the default options here. And by default, it will be 3 classes. 2 features, 3 classes. And then when you plot it, you will get, I mean, the data set, how it look like. Now I'm building my model. I'm building logistic regression from sklearn. So I'm building this model, logistic regression. So not a perceptron. You can try it with a perceptron now, for example. So you can do the same, but you can try with a perceptron. So I'm using a logistic regression model, right? So my model will be logistic regression. I will fit x and 1. It's the same here. I just generated all x values and all y values. I guess it will be 100 points or something for the 3 classes. Please test it, how many points. So we will get x and y. I didn't divide it into a training and testing for simplicity, but now you know it. So when you are writing your program, you need, after generating your data points, you need to divide it into training and testing. Very, very important. But what we are doing here, it's just we need to make it simple, but it's not correct. Simple is not correct. So build your model. Your model will be logistic regression, and now you will fit x and y into your model. I mean, you will fix the model, fit the model using those x and y, and the predictions. I need to get some predictions, right? And the print is a coefficient. How many coefficient we will get here? So I have here 3 classes. It's 3 classes. So should expect that we will get here a vector. In fact, it should be a matrix. So in fact, omega here, it will be like a matrix. One line, it will be omega 1 and omega 2, like 2 column and 1 line for each model. So this one will be model 1, model 2, or class 2, class 3. So it should be something 3 times 2. right? So this one will be the coefficient, model coefficient. So omega values, when it's binary classification problem, it's only two values, omega 1 and omega 2. Now it's a matrix, and the intercept will be a vector. This one will be a vector, so it will be three values, right? So it will be B1, B2, B3, for example, for each model. So you can use this one for plotting the decision line, and as I told you last time, I mean, in this case, if you want to draw the decision line, we will do the same as we did last time. So I generate values for x1. We generate values for x1 using line space from -10 to 10, right? But I have three lines, so I just put it in a for loop, right? So I generated values for x1, and I need to generate values for x2. So x2 will be omega 1 x1 plus b divided by omega 2. So in fact, if the decision line is omega 1 x1 plus omega 2 x2 plus b equals 0, and I generated values for x1. So what will be x2? So this line will be, so x2 will be minus omega 1 x1 plus b divided by omega 2. So this is x2, and just plotting it. And I'm putting it in a for loop. I'm putting it in a for loop because we have three lines. We have three decision lines, right? So after plotting it, what we will get, of course, we got those numbers here. So after plotting, we got those numbers. So we have three classes, and we generated, I mean, for the red class, we generated this red decision line. And if you can see this decision line, it separates the red one from the rest. So it's one versus rest. So the red one, it separates the red class from the rest. The blue one, it separates the blue class from the rest. The green one, it will separate the green class from the rest. So in this case, we can extend a perceptron or a logistic regression using adaptive linear unit, for example, for multi-class classification problem. So it's very simple. And this is the model, how the model will look like. So how the model will look like, it will be like this. So this is the model, in fact. So we have two features, x1 and x2. We will generate one perceptron or one adaptive linear unit for each class. Now the task is to do it for iris dataset. So you have, it's the same code, but instead of working with this blobs, right? You will do it with iris dataset. Here we have three classes. We have two features. It's the same. You can just do the same in case of iris. So now you can extend. Now you can extend. I mean, the perceptron for iris into multi-class classification, because we have three classes. In iris, we have three classes: 0, 1, and 2. So now the task is to extend this one for the iris, and I did it for the iris, and I got those weights, right? So the weights, it's 3 times 2, and we have the bias vector. So now the task is to, please, you can go to this code, this make blobs logistic regression, and just modify this make blobs logistic regression into iris dataset. So just please open this file from GitHub and try to modify it to iris dataset. Run this one first, and after that, try to modify it for iris dataset. So maybe we can have 10 minutes for, but first, do you have any questions? Any questions for that part?
Yes, Ibrahim, I just got a little bit confused. Normally, the last session, we said that the perceptron is used for binary classification.
Yes, correct.
We want to get binary response. And then we use the ADALIN, or the adaptive linear neuron, when we want to have like regression or a continuous response, like the years of experience. But today you were mentioning that, for example, we want to extend from binary classification to multi-class classification using this technique. And then you mentioned again that we can also use it to extend the ADALIN. So how can we use this technique for, why are we mentioning again the ADALIN, the adaptive linear neuron?
Yes, because the adaptive linear unit, it's the same as I can plot it. I will plot the adaptive linear unit and the perceptron. So just
you mean for regression again?
Yes, we can use it for regression and the classification, right?
Okay. Yeah.
Because classification, it's a regression, right? Do you agree with me that classification it's also regression?
Yes, if when we want to put the output as binary, it is a regression. It is a
Yes,
special
because
case of
we can
regression.
just I mean, we use this bucket approach. They call it bucket, or I don't know how they call it, but we can just use a threshold function to just convert it into binary, for example. So I will just clean this one. So for a perceptron, so I will draw it for a perceptron, right? I will draw for a perceptron. So a perceptron will look like this one. We have this one, right? Imagine we have two inputs, x1 and this is the perceptron. We will have here summation, and after that we will apply this hard limb function, correct? So this one, it's a perceptron. In adaptive linear unit, it will be the same, no difference. It will be the same. We'll have here summation. Imagine we have two inputs, x1 and x2. But instead of using this hard limb function or this step function, we will use sigmoid, correct? We'll use this function, correct? And after that, so I will get net here, and I will apply this net to this one. So I will get some output here, right? So this output here, it will be 1 divided by 1 plus exponential minus net, right? And after that, I can put here this, I mean, threshold function. Threshold, so it will be like this one. So I can just add this function here, right? And that is it. So now it's so in fact, so there is no difference between a perceptron and adaptive linear unit, right? Is there any difference? No difference. I mean, the difference is this function. The difference here, it's this function, right? So instead of using this hard limb or step function, we will use a Gaussian function here, right? So this is the only difference. And if we can extend this one to multi-class, we can extend this one to multi-class. And the extension, it's just a concept, and this concept it says that if you have a data set and if you have 3 classes, so maybe we have one class here, we have one class here, and we have maybe a third class. We have a third class here, right? So we have 3 classes. So imagine that this one versus the rest, it's simply just we need to, if I want to, I can consider my data set as two classes now, right? I will assume that my data set will be only, this one will be one class, and this one will be a second class, correct? And in this case, my decision line will be like this one. And you repeat this one for each class. So this is the extension, how we extend one versus rest. So it's just a concept, in fact. It's just a concept. So now I have 3 classes. So I will consider this one as one class 1. And this one will be class 2. So it's a binary classification, correct? So I'm combining all the rest of my data into a second class. So this one will be one class. This one will be another class. So now it's binary classification. And I will repeat this process for the number of classes which we have. So if we have 3 classes, so I will repeat this one. I will put this one in a for loop. We will put it in a for loop and generate one binary classifier for each class. So it will separate this class from the rest. It will separate this one from the rest, and so on. So we will do it like this. So in fact, indeed, it's a binary classification, but it's just a concept or a trick which can help us to extend this binary classifier for multi-class classification problems.
Yes, now it is clearer, but I still have one question. And the question, for example, when we have the iris data set that we want to use for classification, then we can choose between the perceptron or the Adaline. However, if we have the regression, for example, if we have the years of experience or the weather forecast, then we cannot use the perceptron. We have to use the Adaline.
Yes, correct. Yeah, right. Do you know why?
Okay. Yeah, because the first one is a step. Yeah, it will give us like
Yeah.
ones and zero, and we don't want that. However,
and,
the second
and,
one
and
will give us
also,
a continuous.
if it is
But we are not
regression,
going to
maybe
use. But we are not going to use the last part, the one that you have made, the last part of the Adalil. We are not going to use it in weather. We are
in
going to
fact
avoid
we
it.
used this one. We used this one. Do you remember? Y
Yeah, now
equal
it's
x.
clear. Okay, now I got it.
We used this linear function. We used the linear function. So in fact, because when it's unit step, we use it for classification. This one we use it for classification. This one also for classification, in fact. But instead of giving me one class and zero class, for example, it will give me the probability. So it will give me a number here, number between 0 and 1. For example, it will give me a number between 0 and 1. This number between 0 and 1, it will be the probability that this data point belongs to this class. So it could be a number 0.6, which means this data point belongs to this class by 60%, right? So it will give me a probability. And comparing those probability by 0.5, for example, so I can just imagine that it would be like this one. I have this function, and this function will give me probability between 0 and 1, correct? So if I have a data point, coming in, for example, maybe it will be classified as it will give me a number here, right? If this number here, I can just draw a line here, threshold. If this number is greater than 0.5, it means it will be 1. Otherwise, it will be 0. So I have two classes at the end, but I will use a logistic regression function or a sigmoid function to give me the probability that as a number between 0 and 1, right? Instead of using just the unit step. So I can use this unit step. I can use this function directly, right? Or I can use this Gaussian function. So the output here directly will be 0 and 1, right? But if you will use this Gaussian function or logistic regression, for example, instead of giving you 0 and 1, it will give you all numbers between 0 and 1, right? So the output, in fact, here the output, it's just 0 or 1. But in this case here, the output, it's a number between 0 and 1, right? So it's the same, but in case of regression, I cannot use both of them in regression. In regression, I need to use a linear function. We need to use a linear function, which is y equal x. Because if you want to predict, I mean, the income for the next year, it cannot be a number between 0 and 1, but it could be 10 million, for example, or 5 million NOK per year. Imagine. So I need to use a linear function.
Now it is really clear. I was just confused about the use of each one, but now I think now I got it in the correct way. So thank you a lot.
Yeah, thanks a lot, Ahmed. So please, you can just try to go to the code now for this MakePlops logistic regression and try to change it to solve this iris dataset. So if you can go to this GitHub for this link in the screen, can you see it? No, cannot see it. So I will share this one. So can you see my screen? So just please go to this link. Okay, sorry. So please go to this link and try to please go to this link and open this link and try to modify it to iris dataset. Because the iris dataset, we have 3 classes. I mean, so far we have been working with iris as binary classification. And if you remember the code last time, we used only the first 100 points. We used the first 100 points from 0 to 100 because the first 100 points are related to the first 2 classes. Now we need to extend it to the 3 classes. So just select. We have 4 features in iris. We have x1, we have x2, we have x3, we have x4. I mean, you can take 4. I mean, the input it could be 4, no problem, but we will not be able to plot 4 in 2-dimensional space. So you can just select, for example, x1 and x3, for example, as inputs, and you can use the 3 classes. So now we need to solve this problem for 3 classes. and plot the decision line. And I can give you 10 minutes. We can take 10 minutes, for example, break. You drink your coffee and work in the code, and we can meet after 10 minutes. Hello? Okay, should we? Hello, everybody? Did you train your model? Okay. So did you train your model? So now we will extend this perceptron for multi-class classification. It's a perceptron. So we will just make it simple. It's just a perceptron. So we have two input features. We have Seibel length and Seibel width. You can just select petal length and petal width. So I'm selecting petal length and petal width. We have three classes. Now we will use three classes: Setosa, Versicolor, and Virginica. So now we need to build this model for the three classes. So we should expect three models. One for, we call it Y1, for example, one for Y2, one for Y3. We will have two inputs, so we will use two inputs. So each perceptron, it has two inputs and one pipes. So omega 1, omega 2, P1, omega 2, omega 3, and so on. So you can just call it omega 1, 1, omega 1, 2, P1, omega 1, 2, omega 2, 2, omega 1, 3, and omega 2, 3, for example. So now we need to build this model. We need to extend a perceptron for multi-class classification. So did you get your, is it working with you? So now I will go to my my code. I'm sharing it with you now. So I will do the same. I will import data sets from sklearn. I will import Iris. I will load Iris, but in this case I will make some changes. So instead of using the first 100 points, I will just use the whole data set, 150 points. So in this case we are using 150 points, which are corresponding to three classes. For the input features, I will use the third and fourth features. So I will use petal length and petal width. I will, of course, as we mentioned, we need to normalize or standardize my input features. So I will import this one from sklearn in pre-processing, standard scalar. We will import this function, and we will use this function for doing this. But it's not very important to use, in fact, this one. So standard scalar, in fact, it's not very important to use because in fact we can just do it directly. I mean, we can just I mean x standardized x std equal, in fact, x minus mu of x divided by standard deviation of x. So if you want to do it like this one, it's fine, no problem, right? There is no difference at all. So in this case, in fact, each feature, we will be sure that each feature has a mean value of 0 and a standard deviation of 1, right? If you want to normalize, we can just say, okay, if we want to normalize, it will be xn, for example. It will be x minus x mean or minimum of x divided by the range. The range will be maximum of x minus minimum of x. So this one, in fact, it's range, right? So in this case, in fact, all data points will be just, it will be greater than or equal 0, less than or equal 1, right? So now it's normalized. And it's important. Why it's important? For many reasons. For the first reason that all features, because if some features are too large, some features are very small, maybe the neural network will try to classify. It will make classification, but like feature selection. It will make selection, not classify, but it will selection. It will make a selection. And also because of the activation function. So if we have this sigmoid function, do you see? this is the range of inputs, and this is y, for example. So it has this squashing impact in fact. So all those values will be converted. All those values will be converted to 1. And all those negative values will be converted to 0, right? So if we didn't normalize, for example, we will have this problem. We will lose lots of information, in fact, because all those large values will be converted to 1. So if we are talking about income, so the one who has his income here, there will be no difference between him, in fact, and the one who has his input income here. No difference. Both of them will be squashed into 1, which means we are losing information. We are losing too much information. But if you want to keep this information and this variation in your data set, if we can normalize, we will be sure that all data points will be located here. So the big one will be here, large one, small one will be here. So we will keep the variation in our data set, and it will be easy for our model to learn. So we uploaded our data set, right? And as I mentioned here in that part, we just used the whole data points. I mean, last time it was from 0 to 100 for 2 classes. Now we are using the whole data set. We standardized our data set. So this one was the range. Do you see for X? I mean, it's just for one example. For example, it was 1.4 or 0.2. Now when we standardized, it becomes in those values. Now we will split our data set into a testing and a training, right? So the test size is 0.3, which means 30% will be used for testing and 70% will be used for training. We have this one, Stratify. Do you see Stratify? When we use Stratify, we will be sure that our data set will be divided in a way to be balanced. Yes, and it's balanced because we have in the training set, for example, we have 35 class 0. We have 35 class 1, 35 class 2. In the testing data set, we have 15 class 0, 15 class 1, and 15 class 2. So it's balanced data set. So Stratify, it will make it balanced data set. I mean, those simple tricks are important. It will save time later on, and it will give you a model really which is much. So now we are ready to go to the next. So now we just uploaded our data. Now we need to select a model. We will use a perceptron. So I'm selecting here a perceptron. You see? So we are using a perceptron. We are using a perceptron. So we will use here a perceptron. So the perceptron, we need to select number of iterations or number of epochs. It's 20. This is the learning rate. 0.002. I'm selecting a very small number because maybe if it's a big number, it will oscillate around global minimum and it will not converge and it might diverge random state. So this is just basic stuff. And after that, I will train my model using the training data set. So I'm using here X train, Y train. And for prediction, I will do it for the X test. So we will fit the model using the training data set. We have X train, Y train, and we will predict. We will have Y predictions for the test data set because we need to test it. So I need to count the misclassified cases for the test, for example. So misclassified cases, it will be the summation of the cases where Y test not equal to Y predicted, if you want to find the misclassified cases. So I trained the model, and when we trained the model, we have misclassified only 2 misclassified cases in the testing data set. So the model accuracy, in fact, for I guess model, okay. I mean, you will get the same numbers. I mean, we have this function. I mean, the accuracy will be number of cases, total number of cases minus misclassified cases divided by the total number of cases. So this one will be the accuracy. You can get the same number also using this function, model.score, X test, Y test. So in fact, if you want to calculate the error directly, you can do it using this one. or accuracy. So model.score x test y test. You can do it for the training. So model.score x training y training to get this accuracy. So if you want to find the accuracy in the training and the accuracy in the testing, you can use this function directly. So you can do this function in one step, or you can count number of misclassified cases using this approach. I did both of them here to show you that you will get the same number. So model.score, or you can just count number of misclassified cases using this line. Plotting the decision line, we did that several times. We will do it for the grid, right? We will do it for the mesh grid. So as I mentioned last time, we will generate points for x1 and x2. We will use a command which called the mesh grid. So we will generate this grid, and I will apply the model at each point in the grid. I will apply it at each point in the grid, and after that we can plot it in 3D. So finally, this is the decision region for the training and for the testing. Of course, the decision line will be the same, right? The decision line will be the same. The decision line will be the same, if you can see here. But it's here we have the training dataset and testing dataset. And those are the two cases, in fact. We have two misclassified cases. Those are the two misclassified cases. So we have the decision line. So we have this one class, right, for the blue, this one for the green, this one for the magenta. We have here some error. So misclassified samples in the training it's 11, and the accuracy it's 89%. And for the testing, the accuracy looks better. So maybe you need to shuffle the data more, right? So you need to shuffle the data maybe several times before dividing it. So this is a decision region for the training and for the testing dataset. And those are the two cases. We have two misclassified cases, right? So we have the two cases. And we have some overlap here, in fact. So maybe this is a problem because, I mean, we are using a perceptron, and the perceptron will generate a straight line. I mean, the decision line will be straight. So maybe that is why we have, but I mean, the dataset should be easy. Maybe we need to find a model like this one. We need to find something like this one, right? So anyway, so the perceptron will never converge if the classes are not perfectly linearly separable. In Iris dataset, there will be always at least one misclassified sample present in each epoch. It will be impossible because we have some kind of overlap. So it will be hard to find a decision line linearly because it's not exactly linearly separable, in fact. So it will be impossible. And remember here, we use the two features. We use the x1 and x2. If you will use maybe x1, x2, x3, you will generate a plane, and this plane will be, the performance will be much better. So anyway, the model accuracy here for the training, it's 89%, and for the testing, it's 95%. This number, it's 2 divided. So in fact, this accuracy here, it should be 1 minus 2 divided by the total number of classes in the testing. So if it is maybe n, for example, so it will be like this one, n training, and it will be the same for n. 11 divided by the total number of classes in the training data set. So that is this is how can we find the accuracy, model accuracy. Prediction error, it will be 1 minus the model accuracy. So if someone just asks you what is the model, I mean prediction error, of course the prediction error, it will be here 10% or 10.48%. Here it will be 3.45%. So the accuracy equal 1 minus prediction error or vice versa. So is it possible to repeat this problem? I mean, we did it using a perceptron, right? We did this problem using a perceptron. But is it really possible to do it using, I mean, logistic regression? Why not? We can do it using a logistic regression, and we can make comparison. We can make comparison between the two models. As I told you before, the perceptron, it's quite simple. We will have this summing point here. We have here two features. We selected only two features, x1 and x2, right? And after that, we will have this step function, activation function, and we will have y. We extended it for multi-class classification, so should expect three models. So in fact, we should expect three models from the same type. We should expect three models. So this one will be y1, for example, y2, y3, and it's connecting x1 and x2, x1 and x2. So because we're extending it for multi-class classification. So we did it using a perceptron. So can we do it using logistic regression? Yes, why not? So we'll just replace perceptron with a logistic regression. So we can repeat the problem one more time for just exactly the same, but just instead of using a perceptron, you need to change this perceptron into a logistic regression. What is the difference? In logistic regression, we will have this activation function, this Gaussian activation function. So it will be like this one. Right? So we will find the probability that an example belongs to one of the classes. And of course, for multi-class classification, we will use one versus rest strategy or concept. Or so we can go to the slides and modeling class probabilities. Do you want time to run this code? You have also the code. It's called I didn't put a link for it here, so I guess it's perceptron. It's a perceptron for multi-class classification. So maybe I can find it. Yes, we have a perceptron. We have one called the perceptron. I will share it with you. Yes, and I will share the link with you also. So you have the link. And I will add also the link to the slides, maybe. Yeah. So I will run it. So here we used the iris dataset. I used the whole dataset. I used the features, the petal length and petal width. Model accuracy, it's 95%. Those are the weights. Do you see weights and the bias? Because for when we extend it for multi-class, we should have weights as a matrix and the bias as a vector. So now it's one line for each perceptron, in fact. So we have here one line for each perceptron. This is how can we plot the decision line. And you see we have 11 misclassified cases. We have 11 misclassified cases here. So, and of course you can do it for, yes. So I should add maybe this line to, the link to the slides. Yes. So I will just add it here. I'm just adding the link for people to easy to get access to it. So this is the link of. Okay. So now, now I will share with you my. Do you need some time to?
Okay, Ibrahim, I have a question.
Yeah.
That I have a question that in case of when we are applying perceptron model, we are providing Y or labels in the form of zeros, ones, and twos only.
Yes. Yes.
3 classes. But in the lab, we tried to do the same model in the previous class with Ming Tao. And in that, he mentioned that in case of perceptron, we need to provide that the labels in the form of vectors, not just zeros, ones, and twos. For example, zero label would be 100 vector, and the label 1 could be 010 vector, and the label 2 could be 001 vector.
Yeah, yeah.
So
we call it one hot
this?
encoding. Yeah, yeah, correct. We call it one hot encoding.
So is it? But in this model, we haven't done this. Is that library sklearn take care of it itself?
What did you say?
Because he said that we need to convert the labels into the vectors. It is compulsory in the case of perceptron, but here we are not doing it. Does the library or the model take care of it itself?
Yes, yes,
question.
I guess yes, yes. Maybe, but you, I mean, because it's a 0, 1, 2. You are right. It's a 0, 1, 2. So maybe she is doing this one hot encoding internally, for example, right?
All right.
Yeah, because in the maybe it take care of it in the in the training function in fit model.fit, right? But if you want to do it externally, you can just do one hot encoding, right? We need to test it in fact. So just to try to test it. So now we are using it as a vector 0, 1. It's just a label, right? It's just a label. So I don't know how the library will deal with it, but if you want to do it as a one hot encoding, it's fine, right? It's okay.
Yeah, it must be taking care of it because he used Keras, and in that when we tried these labels 0s, 1s, and 2s, it gave an error. It said the library gave an error, but now we are not getting an error. Probably the library
because in
itself
Keras it must be one hot encoding, right?
Yeah.
Yeah, yeah.
Okay.
So
thank you very much. I got my answer.
But it's in fact it's just a label, right? We are not because when it's extending it to this multi-class classification, I mean, you can test it in the first example when we used it in binary classification, because in the binary classification, the first class was 0 and the second class was 1. Try it with the first class, which is 0, and the second class, which is 1, right? So it might, I mean, normalize it, for example, so all numbers between 0 and 1, for example. So the class which is 1, it will be 0.5. So I don't know how it deal with it internally, in fact. But you can just test, I mean, the first, and today we had the first example. We have two classes, 0 and 1. Try to take the first class and the last class, which is 0 and 2, and check if it will give you an error or not. Yes. So we need to talk about, I mean, modeling a class probabilities by logistic regression. I mean, in logistic regression, we have this Gaussian function, right? We have this Gaussian function in logistic regression. This one in linear regression. So if I have a data points, so logistic regression is one of the most popular machine learning algorithms in industry. It's very popular, in fact, and it's in classification. We can use it for, it can perform classification for linearly separable classes when we have two classes as yes and no, true and false, for example, instead of predicting something continuous. If we need to predict something continuous, we need to use linear function. And instead of fitting a line to the data, we fit S-shaped logistic function. So we use this L-shape. So this one, it's linear regression. Imagine we have a data set like this one. This is one class which is 0, for example. So we have this class, for example. and we have another class. So we have two classes. So it will be impossible, in fact, to use linear regression here. We can use a linear regression. So maybe this linear regression, it will give us a line like this one, and all points which are above it, it will be one class. So those one will be one class. Those points will be another class. Do you see? This is the case in linear regression. Points which are located above will be positive class. This one will be positive. This one will be negative class. So if you can see it now, we cannot use linear regression with such data set. But if you can fit an S-shaped logistic function, it will be much better now, correct? And in this case, it will predict the probability that this point belongs to this class. For example, maybe I have a point here, correct? So we will find the probability. So maybe this probability will be 80%. Here it will be 85%, 90%, 100%, and so on. Right? And we can use a threshold value, as I mentioned to Ahmed today. We can use a threshold value because, I mean, the output here, it will be continuous value between 0 and 1. So we can compare those probabilities with 0.5 as a threshold value. And all probabilities which are above 0.1, it will be 1. It will be classified as 1. So in this case, we can draw this line. So using this threshold value, we can draw this line. So at the end also, we will convert it into two classes, 0 class.
Ibrahim,
and 1
we cannot see what you are drawing.
Sure.
You have to share. Yeah, no. You have to share with the Blackboard.
Okay. Okay, sorry. Yes.
Thank you.
Yeah, is it fine now? Can you see it?
No, it is still. Yeah, I think we can. No.
Is this one?
These are the slides. Yeah, the slides.
Okay. So I mean we have this logistic regression. We will fit it into our data because it will be more suitable, in fact, compared to this straight line. If we have this straight line, we will have a problem. All data points above it, it will be one class. All data points below it, it will be another class. And if we got some data points in the future here, it will be classified negative, but it should be positive, in fact, because it's y equal 1, right? So in fact, my data points here, it's two classes. Y equals 0, this is one class. Y equal 1, it's another class. So I have my data points in reality, it's just divided like this, 0 class and 1 class. But if you try to fit a linear regression model here, maybe it will be hard to find a line, but maybe it's okay. Maybe I can select this line, right? I will select this line. All those data points will be classified as 1. All those data points will be classified as 0, correct? But in the future, what will happen if I got a data point here? It will be misclassified as negative. So I will do it. I will do it here, and I will do it in. I will try to share. Okay, I will share this whiteboard. So I want to clear it. So so imagine that we have data like this one. This one, it's x1 or x and y, right? And we have two classes. It's here y equal 0 and here y equal 1. And I have some data points. I have data points here, which is classified as 1, right? And I have another data points here, which is classified as 0. And now I want to fit a linear model to solve this problem, because I need to build a model which will classify those data points into two classes. So so this is one class, which is class 0, and this one, it's another class, which is class, this one 0, and this one it's 1, right? We have two classes. We need to fit a linear line. So maybe I will draw a line like this one. Maybe this line will be okay. I will draw this line. I will select this line. Is it okay? Do you agree with me that this line will give us 100% accuracy? So this line, in fact, it will give us 100% accuracy. All those data points will be classified as 1. All those data points will be classified as 0. So the accuracy will be 100%. Right? But imagine that in the future, we will get some few data points here. What will be the situation for those data points? Will they be classified as 1 or 0?
They will be misclassified.
Misclassified because this is positive. All points above the line will be positive. All points below the line will be negative. So in fact, those one will be misclassified. So in fact, I can use a linear model, but this linear model today for the data set which we have, it will be fine because I can find this beautiful line which will classify it correctly. But in the future, it will be a problem because I got some points which are, it looks like an outlier, but it's a class 1 in fact. It's a different X value, but it should be class 1. It's class 1, but now it's not classified as 1. So this model will not help us to classify it. So we will try a different approach. So now we will draw the same data points, right? This is class, this is y equal 1. This one, it's y equal 0. We will draw the same data points. I have some data points here. And in the future, we will get some, outliers here, right, in the future. And I have some data points here, which is class 0. So instead of using linear model, we will use Gaussian. We will use this logistic regression model. So in this case, I will select this one. So what do you think? Which one will be more accurate? So which one is, because it has some kind of non-linearity, in fact, is this one, right? So instead of using linear regression or linear model, I will use this Gaussian function or logistic regression function. And this function, it's simple. It's just y equal 1 plus exponential minus omega x or omega x plus b, for example, right? So this is a function which we will use logistic regression. So in fact, logistic regression, it's more useful, it's more popular because it solves this kind of problem. If I will select a linear, just make comparison. If I will select this line, so imagine that I'm selecting this straight line. This line, it's okay now, but we will have those data points will be misclassified if I used a linear model. But if we will use logistic regression, we will be sure that my model, the performance of my model, will take care of those points in the future. So this one, it's more popular, and it's much the performance should be much better than a linear model. And it will be the same because when we use this linear model, we convert those one into we convert it into this yes and no, right? Activation function, sorry. So it will be just yes and no, but we will take care of it also because we can just draw a line here at 0.5, and all probabilities above 0.5 will be classified as 1, and all probabilities below 0.5 will be classified as class 0. So this one, in fact, it's very important, and I will just go back to my my slides. So now we need to. So in the logistic regression, we will have positive class or yes class or true class, and the negative class, which is no and false. For example, logistic regression, we can use it in diagnosis, for example. So you need to build a system. You collect a sample or you collect some features from patients, and you want to build a system for medical diagnosis. It should decide if someone has corona, for example, or does not have corona, based on some symptoms. So maybe not all people will be in the same category, in the same region, for example. So in this case, we need a model which can take care of those outliers. So it can be also extended into multi-class classification. It's the same. We can extend it into multi-class classification. If we have 3 classes, 4 classes, 5 classes, it will be exactly the same. So, and it's about likelihood. It's about likelihood of an event. For example, you have, I mean, this example, it's our studied and the exam results. So you have an exam, for example, and we need to measure how many people, how many students, how many hours they study, for example. So people who are studying 29, it's non-linear. There is no linear relationship here, in fact, because it's different from one to another. So, for example, it's pass and fail. I mean, results here will be pass and fail. So the one who studied 28 hours, he can pass. 33, he will pass. 15, he will not be able to pass. 29, he cannot pass. But you see, 28 can pass, right? So it's not linear relationship. It's a kind of non-linear relationship, which cannot be described by a straight line, but we need a regression model to fit those data points because of those irregularities, for example, in my data points. So when we draw those data points, if you want to fit a straight line, it will be a problem because those data points, they are zero. I know that they are zero class, they cannot pass, but now they will be classified as passing because they are above the line. Those data points, it's okay. So these data points, it's fine. Sorry, I need to. So these data points would be classified as pass, right? One pass. This one also will be classified. This one cannot pass the exam. This one cannot pass the exam. So when you fit a straight line, I mean the accuracy, we will have some, problem in the accuracy. You will not get 100% accuracy, for example, or 95%, 96% accuracy because of this situation. And as I mentioned, if you got a case here in the future, it would be misclassified, right? If you got a case here in the future, it would be, no, this one will be correctly classified. This one will be misclassified. So it's hard, in fact, to fit a straight line in our data set, right? Of course, you can fit different lines. Maybe this line is okay for this data set. In the future, I got a new data point. So you need to get a different line. In fact, we need to update the model. So I have a data point. I have my data now at the moment, and I got this red line. But in the future, this line will be a problem. So I need to retrain my model. When we're adding outliers, we need to retrain the model one more time, maybe, to consider future cases to generate this. You see, it's a big difference, a huge difference, in fact. So just adding an outlier, you will get a different line, right? So how can we solve this problem? We can solve it using a logistic regression. So logistic regression, it will be 1 divided by 1 plus exponential minus net. And we need to have a hypothesis, for example. So when value of j, for example, it's greater than 0.5, it should be classified as 1, and otherwise it should be classified as 0. So anyway, we will get this line anyway. We will have this line all time. We will get this line because this line, it's omega transpose multiplied by x. So we will get this line all time. We will apply this net to this function, 1 divided by 1 plus exponential minus net. And we need to have a hypothesis because we need to get some classes. So the hypothesis will be when j greater than 0.5, it will be classified as 1. Otherwise, it will be classified as 0. So now we have 2 classes. So this one will be 0 class. This one will be 1 class. So how can we implement it? It's easy also from sklearn linear model. We need to import logistic regression model. We need to import. So it's the same as a perceptron, but instead of using hard-lim function, because in perceptron we use this function, right? We use this function in hard-lim in perceptron, but in this case we will use this function here, right? We will use this Gaussian function or logistic regression function. So I try to fit it for this simple function, and it's just, just to try to generate any data points, or just to do it for you can do it, for example, for iris data set, and just do it. So now I have those data points, I will fit a logistic regression model. We will get this green one, right? We need to propose a hypothesis. So the hypothesis will be all probabilities greater than or equal 0.5 will be classified as 1. Otherwise, it will be 0. Right? So this class here. So to the left side, all points to the left side will be classified as 1. All points to the right-hand side, it will be classified as, sorry, right will be classified as 1, and to the left will be classified as 0. Yes. So this is the model. How the model logistic regression? We have also this one in GitHub. You can try it. But this is the model. How the model will look like. So you have number of inputs, x1, x2, x3, and xn. All inputs are connected with this with the perceptron or the neuron, for example, using some weight value. This one it's for bias. This one it's for bias. So so this one it's for this one it's bias. So finally we will get here net equal omega transpose x, or omega 1 x1 plus omega 2 x2 plus omega n xn plus omega 0 or b. So this is a decision line. In fact, it's linear decision line. We will apply this value to this activation function, right? So we will get this. I mean, it will be g net equal 1 divided by 1 plus exponential minus net. And after that, we will compare this one to 0.5, right? So we will, to get this unit step function. So we can, at the end, we will get, at the end here, we will get 0 class and 1 class, 1 and 0, right? 1 when g net or g net greater than or equal 0, and this one otherwise. Yes. So any questions? I can see people, some comments. Yes, you can use it, but we will not call it a perceptron. When we use it with a perceptron, we will not call it a perceptron. We will call it adaptive linear unit, or no, adaptive linear unit is the straight line. It's with a perceptron, just use a different, yes, use a logistic regression, but usually perceptrons they call, because it's a historical name, in fact. So a perceptron, they call it a perceptron when it's binary activation function or step activation function. But when it's a logistic regression, just call it logistic regression model. So they call this one a perceptron, and when you use different activation functions, they call it logistic regression. But it's not regression. Also, the name is not correct. Logistic regression. It's logistic regression, but in fact, we use it for classification. So you can just say it's logistic regression for classification. So maybe this logistic regression, it came from statistics, but a perceptron, people know that when it's a perceptron, we have a step activation function, and then when it's a logistic regression, the activation function is this logistic function or this Gaussian function, for example. So, okay, I'm confused between model, activation function, and the decision boundary. No, it's not mixed, Muhammad. It's not mixed, Muhammad, right? Because the decision line, this line, right? We have net equal omega transpose x plus b, for example. This is the decision line, right? So this is the decision line which we will generate. And the value.
I cannot see what you're writing.
You cannot see my screen?
Yeah, we cannot see.
Okay. You should see this one, right? You should. Can you see it now, Muhammad? Can you see it?
Yeah, I can see now.
Okay. So I mean this is the logistic regression classifier. It's also, I mean, the name, it's tricky because it's a logistic regression, but it's a classifier. Do you see?
But Ibrahim, are you drawing something? Because I cannot see what you're writing. I cannot see what you're writing.
You cannot see any red stuff.
I can see, but I was thinking that you were writing at the moment. Yes. I cannot see that.
Okay. So I mean, can you see it now?
Yeah, I can see.
So we have this regression. we have this regression. It's not regression, in fact, but it's a classifier, but they call it logistic regression classifier. So it's the same as a perceptron. So if we change it, if we remove this activation function, and if we send this one back here, it will be a perceptron, right? So if we deleted this line and we calculated the error here after the unit step function, it will be a perceptron. But we replaced the unit step function with Gaussian activation function here, right? We calculate the error here for updating the weights, and we use this unit step for just classification. I need to make decisions. So when probability is greater than 0.5, we can just say it belongs to class 1, otherwise it belongs to class 0.
And one last thing, the decision line is always that net is equal to 0.
Net equal to 0 on the line.
Okay.
Right. So on the line it's equal 0. In fact, above the line it's positive. Below the line it's negative.
All right.
Mm-hmm. So the decision line, in fact, it's net equal 0 if the point will be located on the line itself. And that is how we draw the decision line, because when we want to draw this straight line, for example, we just assume that omega, if it is omega 1 x1, so if we need to plot so the decision line, so we can just say omega 1 x1 plus omega 2 x2 plus b equals 0, right? So we will get values for x1. I need to find x2. So x2 will be minus omega 1 x1 plus b divided by omega 2. So it's equal 0, and on the line it's equal 0. So we will get, now we have the value of, we can find the value of x2 and we can plot the decision line.
Yeah, but this decision line will always be a linear one, right? Irrespective of the function, if it is a logistic or unit step activation function.
Yes, correct. You are right. So it's just.
But in the example you just gave right now, when you were plotting the models, you were saying that if we plot if we fit a linear model, it would be a straight line, and if we fit a regression model, it would be this curved line.
No, it will not be a curved line. I mean, you have x1 and x2. So if you have inputs, it's a linear function. If it's x1 and x2, it will be linear function all time. If you want to make it non-linear, so maybe we need to add some new features. Maybe I need to add x1 square and x2 square to make it curve. I mean a curve, not a straight line.
Okay, can you move to the next slide, please?
Do you see this decision region? I know you are talking about this decision region. Do you see it?
Yeah, I see it. But no, I was talking when you were discussing the model actually. Can you move to that slide, please?
No, this line will be straight all time. It's in multi-classification. This line will be straight all time as long as it's function of x1 and x2. Because this line, in fact, the equation of this line, it's, for example, it's omega 1 x1 plus omega 2 x2 plus b equals 0, right? So this line will be straight all time. It will be straight line all time. But if you want to make it a curve or something, maybe we need to add some non-linearity to the line, right? So how can we do this? Maybe we need to use x1 squared. We can just assume that I can add new features. For example, if it is complex to hard to separate the two classes if they are overlapped. So in this case, we can add, for example, I have x1 and I have x2. Maybe I need to add x1 square and x2 square, correct? So when you add x1 squared and you will get a complex decision line. You will get a curvy line, right?
Right. So there were some misclassified predictions. So one way is to we can change the linear decision line to the polynomial or
polynomial. It will be higher polynomial. So we need to add higher polynomials. I mean, we need to add. I mean, higher. Yes.
And one way to improve the model is to change the model entirely from linear regression or perceptron to logistic regression, right?
Yes. I mean, logistic regression. It will just the output will be a probability instead of just. And it will be much better for dealing with some cases with some problems, as I mentioned, as I described, right? So I
All
just
right. Thank
this is
you.
a- so if you have some data points, it will be like this one. And this is another class, but what will happen if we got a data point in the future here? So how we will classify it? So for some data sets, it will be much better. The performance will be much better with logistic regression compared to linear regression. Because if I have this
Alright.
straight line here, I find this line and I'm happy with it at the moment, but in the future you will get a data point here. So according to this line, this data point will be misclassified. But if you are using a logistic regression, this point will be correctly classified. So you need to select, which one should be used for what? For linear regression, we have some restrictions, but also remember, for logistic regression, when we are plotting the decision line, we will plot also, the linear, the straight line. We are not plotting anything else. We're still plotting the line, right? But the decision will be different. We will have the straight line, but the data point, how it will be classified, is it 1 or 0? So is it still misclassified? So you can do it. In fact, it will be good home assignment, Muhammad. In fact, so you can generate those data points, right? You can create customized data set like this one, and try to fit it using a linear regression model and a logistic regression model, and in the two cases plot the decision line, and see if check if some misclassified cases, misclassified examples in the linear regression, how it will look like in the logistic regression. So you can just make comparison between the two cases. So you can generate the data point. It's easy. Like this one, it's just x and y, and it's pass and fail, and you have some it's hours. In the x-axis, it's studied hours, for example. So you can just generate these data points. It's the example which we did here, right? I don't know, where is it? This example, you can just do it for this example. So just to generate a data point which looks like okay, and try to fit a linear model, and try to fit a regression model, and try to see what is the difference. Is there any difference in accuracy, performance, and so on? And make comparison between the two cases. Yes. So the decision boundary, I'm talking here also about the decision boundary, because when we are plotting, what will be the decision boundary? So this one will be the decision boundary, right? But the decision will be different. This is a decision boundary, but will it be class 1 or class 2? This is a point. But when we are plotting, we will plot this decision line. This is our decision line, correct? But this is a decision. This is a decision line, and this one will be the decision. If it will be 1 or 0, right? So according to the linear, if you will not use this Gaussian function, logistic regression, maybe a data point, instead of being classified as 1, it will be misclassified as 0, and vice versa. So you will have the same decision line, but the point will be correctly classified.
All right, now I got it. Thank you.
Yes. What about linearly inseparable data sets? We are talking about, it should be separable data sets. If you want to use a regression model, linear regression model, if you want to use linear model, so the data set should be linearly separable. What if it is inseparable? So just as you mentioned, we just need to add higher order features to make the decision line as a polynomial, right? So imagine you have a data set, and also, by the way, you can generate this data set from sklearn. So we have here two classes. We have its data point also generated in x1 and x2. We have two features. We have x1, we have x2. We have the red one, it's a class 1, and the blue one, it's a class 0, right? So of course it's inseparable, right? The data point. So if we need to generate a decision line which is a line, we cannot. It's impossible, right? So if I selected this one, the accuracy will be 50%. How can we solve it? We can solve it using linear model by adding a new dimension, higher order features. If we can add higher order features to the data set, maybe it will be easy to classify it. using a perceptron, using a linear model, right? So how can we do this? My features are x1 and x2. We have x1, we have x2. We just need to add higher order features. So imagine we can just add x1 squared plus x2 squared. Or you can add x1 squared and x2 squared, so you can add 2 features. But x1, we assume that we will add here, x1 squared plus x2 squared. So we added this higher order features. So instead of working, so now instead of building a model, because it's impossible, if I will use x1 and the x2, it will be impossible to classify it, right? It will be impossible using a perceptron. But by adding, we call it feature engineering, right? It's feature engineering, or just adding a new features, creating a new feature. So we will add x3 here. When we add x3, so the decision line will look like this one. We will have here omega 1 x1, omega 2 x2, omega 3 x3, correct? Plus b. So the decision line will be omega 1 x1 plus omega 2 x2 plus omega 3 multiplied by x1 squared plus omega 2 squared equals 0, right? So imagine that omega 1 and omega 2 will be zeros. Sorry, we need to add here b. Sorry, I just need to I need to add here b plus b equals 0, right? So imagine omega 1 equals 0 and omega 2 equals 0, and imagine omega 3 equal 1. So what will happen? This equation will be omega 1 squared plus omega 2 squared plus b equals 0, right? What is this equation? Yeah, it's equation of a circle, correct? So if you can select the value of b, maybe you can create a decision line which will look like this one. You will get this one. Do you see? So in fact, this one will be 1 class. Maybe it's 1 class 1. And the rest will be 0. So all points which are located inside the circle will be 1, and the other points outside will be class 0. So now it's a linear model. We are still using a perceptron, but we can use this perceptron for classifying a linearly inseparable data set by adding higher order features. So by adding x1 squared and x2 squared, and if you want to plot it in three-dimensional space, it will look like this one. We have x1 here, x2. This one it's x3. Sorry, this one it's x3. Right? So now we can have a plane. We can find a plane which will separate those data points. So we can find this one, and we will have good. I mean, now we are solving the problem using those feature engineering. Skills, and by adding those higher order features, we can create a decision line which is a circle. You just call it a decision boundary. We will not call it a decision line. We'll just call it a decision boundary. So we can create this one, and all points which are located inside the circle, it will be class red class or class 1, and otherwise it will be 0. So now we can solve an inseparable problem using a perceptron. So now for logistic regression model, if we need to use so do you see here? So the decision line will be the same. We have the decision line omega 1 x1 plus omega 2 x2 plus omega 3 x3, or omega 3 x1 squared plus x2 squared. So just adding those higher order polynomials will make it easy. And finally, because I solved it and we got different, but you can try it. You can set omega 1 x equals 0 and omega 2 equal 0 and omega 3 equal 1, for example, and try to plot try to find a value for b, right, which will generate a circle instead of this plane, for example. So it will be easy to solve it. We had also this GitHub code for it, non-separable data set, but try to play with it. Try to make something more, looks much better. So try to do something. So for example, instead of, I can just use it like this one. I can just use very simple single input, maybe, or 2 inputs, for example, x1 squared and the x2 squared, because in this case it will be oval, not circle. We have here the bias. We have here, we have this one. We have here logistic regression. We have here the decision. So in fact, instead, in this case, and according to the value of omega 1, omega 2, and b, instead of getting a circle, maybe we can get something like this one. So try to do it. So try to do this one, for example. You can make it also as a home assignment for this week, for example, and try to solve this problem using higher order features. And instead of using x1 and x2, we can use x1 squared and x2 squared as two inputs, and just use a regression model and try to plot the decision line. How the decision line will look like. It will be a very good problem, in fact. So this is the logistic regression for iris example. Yes, we need to do it for iris. As I mentioned last time, we did perceptron. I mean, if you want to do it for iris, you just need to replace a perceptron with logistic regression. We need to use a logistic regression here. And we will also standardize our data set or normalize. We will use the whole data set in this case. So we will use the 4 inputs. I used the full data set, right? So now I'm using x1 and x2. We have 4 columns. We will use x1, x2, x3, and x4. So we have 4 inputs. And we have 3 classes, right? We have 3 classes. So if you will use logistic regression, in fact, and if we not to plot it, so we will have 3. We will create 3 models. One, we call it y1 or t1, y2, y3. We will have here 4 inputs. We have x1, x2, x3, and x4. So just make all those connections, right? Make all those connections. Now it should be fine, right? So, okay. So it will be like this one. So using logistic regression, you can just make comparison because Ahmed, for example, or if you want to make comparison between logistic regression and a perceptron, we solved it for a perceptron and for a logistic regression, and you can just compare what is there any difference in the performance. So as an assignment, implement logistic regression. So convert adaptive linear unit into a logistic regression. I mean I asked you to implement it step by step instead of using sklearn, for example. But this one from KSLearn, and if you can go to this code, for example, you can see if I don't know if I plot here the decision boundary. So I will share the code with you. Okay. Where is this one? Okay. So do you see this one? We will run it. We uploaded the data, used the whole data set. We standardized all our data sets, and I don't know, I didn't plot the decision boundary, in fact. And those are the weights. So those are the weights and the bias. This is the weights, because we have, in this case, we have 3 classes. We have 4 inputs, right? Do you see this one? It's 3 times 4. So this matrix, it's 3 times 4. This one, it's 3 times 4. Sorry. Oh. So this one, it's 3 times 4. So we will have 3 lines times 4 column. 4 column because we have 4 features, and the 3 lines because we have 3 models. And the bias also we will have 3 values, 1, 2, 3. And the accuracy here, it's prediction error. It's very small. It's 2.6%, right? 2.6%, which means the accuracy is 98% or 97.4%. Number of misclassified cases is 4 cases, right? So the accuracy is very high. So I didn't compare it with perceptron, but you can compare it with a perceptron. So as I told you here, so this one, we have here 3 values. We have here 4 values. It's 4 values because we have 4 features, and the 3 because we have 3 models. And the 4 for the bias, we have also 3 values, 1 for each perceptron or each logistic regression model. So now we can extend it into a logistic regression model. So the accuracy here is 98%. You need to plot, I guess, Muhammad Saad, please, you can plot the decision line and see what is the difference. I mean, if we can compare it with a perceptron, what was the accuracy when it's a perceptron? So the accuracy here was 95%. I mean, the other one, it's 98%. So, but I wish if you can just, we have this decision region. We plot those decision boundaries for a perceptron, right? Draw this one more time for logistic regression. We have here number of cases, misclassified number of cases. We have 11 here and it's 2 here. So try to test the other one and make comparison. But the accuracy there was 98%. So the accuracy in logistic regression was 98%. So what we are missing here is to draw the decision lines and how the decision line look like, right? Also, this problem, we need to try this problem in fact. So in this linearly inseparable data set. So please, if you can write down, we need to have this one also as a home assignment. So you need to generate a data. You need to generate a data points. You need to generate a data set. For this one, for this example, we need to plot this decision boundary. We need to find this one as a circle. So, and as I told you, you can just make it very simple, just using x1 square and x2 square as an inputs. You will find the value of omega 1 and omega 2. It will be easy to plot it in 2-dimensional space, right? It will be nice to plot it in 2-dimensional space using x1 square and x2 square. And of course, it's okay. So instead of working with x1 and x2, I have a new feature set. And this new feature set, it will consist of x1 square and x2 square. Yes. Okay, so it's Iris again using yeah, no, I did the code by step by step. So if you want to implement logistic regression, so I just wrote this class for logistic regression if you want to do it. So we can use logistic regression from sklearn. So if you want to do it from sklearn, we need to import sklearn models or and import logistic regression. We need to check it. Yes, it's linear model. sklearn.linear model. So this one, it's not. So you can import logistic regression from sklearn linear model. Still, they call it linear model, right? We are using regression activation function, but we still call it linear model, right? So you can do it from importing it from sklearn, or you can write it by yourself, write a class for it. So here we have a class for it, logistic regression. We define number of epochs, learning rate, I mean random state. This one for training, and we will run it for number of epochs. First, we initialize weights by random numbers. So we initialize this one, the weights, and it's +1 because of the bias, right? Number of inputs plus bias. And we just calculate the net. First, we calculate net, right? So net, it's omega x plus b. This one, it's omega x plus b. We have here dot products. So the output, we apply this function. So the output will be 1 divided by 1 plus exponential minus x net. And after that, we calculate the error, and we just update the weights. We update the weights and the bias. We calculate the error, mean error each epoch, and we repeat this process until we converge. And this one for prediction, we calculate net, and we apply this net value into the logistic function to find the output. And if you want to apply, look, this one here, this is a threshold function. So from this one, we will have this curve, we will have this function, right? And this is 0.5, the threshold value. So all values above 0.5, it will be converted into 1, and below it, it will be converted into 0 using this function, this line. So now how you can, if you want to do it step by step, if you want to implement it, and just I'm doing it for, and we got very good results as well. So it's the same. There is no difference in fact. And this is the prediction error per epoch if you want to plot it. So we started at some point, we change the weight values. It could go up and it would go down, for example, right? Until we converge at some point here. And this is the decision line which separates the two classes, one class and zero class. So yeah, AltArc is it okay so far? Do you want to take some few minutes break, 5 minutes before going to the confusion matrix? Or do you have any questions? Yes, Muhammad, please. Okay, we will take break. We will take break 10 minutes. So take your coffee and please just we need to try this inseparable data set. We try to train it using different higher order features. Higher order features, it saves us, in fact. There are many problems which is non-separable, and if you can work a little bit with the features, you can convert it into separable data set and just solve it using simple linear regression model or a perceptron. So please we will take 10 minutes break. We will meet again at 11:40. Thank you very much. Hello, hello everybody. So now after, okay. Yes, great, Muhammad. So after there is a pipeline in machine learning. There is a pipeline. First, we need to work with the data. So far we just did very simple stuff with the data, for example, like normalization or standardization, for example. But it's very standard to do this. You need to visualize your data set before building your model, and after that, model selections, training the model, validation your model, and fine-tuning your model parameters, and test your model. And after that, we need to evaluate the model. How can we make evaluation of our model? So one way for doing this is to use confusion matrix. So the perceptron, the accuracy is much higher. So this is really very good, Muhammad. So Muhammad has been trying to use a perceptron for and logistic regression with Iris dataset, and the accuracy for the perceptron it was 95.6, and for logistic regression it was 97.8%. And of course, it will be obvious also from more complex data sets. So thanks, Mohammed. So the confusion matrix, it's a table that is often used to describe the performance of a classification model. We don't use it for regression, but we use it for regression. You can use mean square error, mean absolute error. So you can use any score for describing the prediction, regression accuracy of your model, for example. But in case of classification models, we use confusion matrix. So the confusion matrix, it's a table which is used to describe the performance of a classification model or a classifier on a set of test data for which the true values are known. So we have a test data set, which is a model never seen before, and we need to use the confusion matrix to describe the performance of the model. So in this confusion matrix, we have actual class and the predicted class. So imagine it's binary classification problem. So we have some positive class which has been classified as positive. If it is positive, classified as positive. So if it is positive, classified as positive, we call it true positive. So someone has a disease, and he has been classified as predicted as having a disease, right? So the model was able to classify him as having a disease, for example. So he is true positive. Or someone who should get a loan from the bank, and the model said yes, he should get the loan from the bank. So we call it true positive. And when it's positive and it's misclassified as negative, so we call it false negative, right? So this one, he is positive, a patient is positive, but he will be classified as negative, does not have the disease. So in this case, we call it false negative. It's false negative. And when it's false negative, we call it type 2 error. When it's false negative, we call it type 2 error. On the other side, we have negative classes, a negative class. So if a negative class is misclassified as positive, we call it false positive, and it's type 1 error. Imagine you build a model to make prediction of a disease, for example, the medical diagnosis. So someone is negative, does not have the disease, but he was misclassified as positive. So we call it type 1 error. So maybe we will give him medication which he should not take. So we call it type 1 error. He is positive, but he was misclassified as negative. He has a disease, but we classified him as negative. Dangerous than type 1 error. So type 1 error, he does not have a disease, but he was. So maybe we will give him a medication which he should not take, for example. So it's And we have some other classes which is negative, and he was classified as negative. So we call it true negative. So numbers across this diagonal is to maximize numbers across this diagonal. We need to maximize true positive and then maximize true negative, right? We need to maximize numbers located across this diagonal. The summation of true positive and false positive, it's, I mean, we have total positive here. We have the total positive, total negative, actual negative, and this one, it's the total positive, which is total positive, which has been classified as positive, right? Minimize type 1 error, try to minimize type 2 error, try to maximize true positive cases and the true negative cases.
Ibrahim, can you please repeat the last few seconds, because your voice was did stop.
What, Ahmed?
We couldn't hear you for the last 20 seconds to 30 seconds. Can you repeat?
Okay. Okay, so one more time. Maybe this one is, I need to get closer to me. So I mean, we use this confusion map. Can you hear me now, Ahmed, better?
Yes.
Okay. So the confusion matrix, in fact, we use it to describe the performance of any classifier. In case of regression model, we need to use other score values. Maybe you can use mean square error, mean absolute error, and so on. So in case of classification, imagine that we have binary classification problem. So we have two classes, positive class and negative class. So actual classes we have two groups of patients. For example, some of those patients, they have a disease, some of them, they don't have it. And we build a classifier using some features to make those predictions. So a number of positive cases, which is classified as positive, we call it true positive. Number of negative cases, which has been correctly classified as negative, we call it true negative. Some of those positive cases will be misclassified as negative, right? So some of those positive cases will be misclassified as negative. So in this case, we'll call it false negative. False negative, we call it type 2 error. Some of the negative cases will be misclassified as positive cases. And when it's misclassified as positive, we call it false positive, and we call it type 1 error. In medical, for example, in medicine, I mean, type 1 error and the type 2 errors, both, of course, we need to minimize as much as possible. But type 2 error, usually, it's more dangerous than type 1 error. Type 2 error means you have a patient who has a disease, but he was misclassified as negative, right? So in this case, we will just leave him. We will ask him to go home without any medications or any treatment. So this one is very dangerous, in fact, type 2 error. Type 1 error, you have a patient who is negative, but he was misclassified as positive. So maybe you will give him more medications. You will give him medication which he should not take until you make new analysis and a new checkup and stuff like this. So the type 1 error, it's not dangerous compared to type 2 error, but type 2 error, it's more dangerous. Very, very dangerous case, because you have a patient who has a disease. You have someone who has coronavirus, for example, and you just told him, no, you are negative. He has corona, but you told him you are negative. So he just keep walking and going here and there, go to classroom, go to cinema, go to swimming, and so on. And distribute corona, among people. So this is very dangerous. But but type 1 error, he does not have a corona, but you just misclassified him as positive. You told him, no, you are positive. So you need to stay at home for 2 weeks. So he will not harm anyone, in fact. He will just stay at home for 2 weeks. Maybe he will feel some depression or something. He is okay, but he was misclassified as positive. So you can just compare, you can know which one is more dangerous, in fact. So type 2 error, it's more dangerous than type 1 error. In machine learning, we try to use an optimizer to adjust our weight values in a way to maximize numbers across diagonal, this diagonal. So we need to maximize numbers here across this diagonal and minimize numbers across this diagonal, right? We need to minimize all types of errors. false positive and false negative. So we try to minimize false positive, which is type 1 error, and the false negative, which is type 2 error. And at the same time, we need to maximize true positive and true negative. From this, I mean, confusion matrix, you will get sensitivity, you will get specificity, you will get accuracy. Accuracy, it's easy. It's a true positive plus true negative divided by the total number. So the accuracy, it's okay. It's easy to understand it. So the accuracy will be true positive plus true negative divided by all classes by n, for example. True positive plus true negative, false positive plus false negative, right? And the definitions of, I mean, the other things are as mentioned here. This is the accuracy. If you want to get error, it will be 1 minus accuracy. So if we calculated accuracy and if you want to find error, so error will be 1 minus accuracy. Correct? So imagine the accuracy, it's 0.9%. So in this case, the error will be 10%, right? So basic terms of confusion matrix, true positive. I mean, these are the cases in which we predict yes. So they have the disease and they do have the disease, true positive. So you have a patient who has a disease and he has been predicted as having a disease. This is okay. True negative, it's fine. We predict no, and they don't have the disease. So this one is fine. False positive, this is a problem, false positive. We call it type 1 error. So false positive, we predict yes, but they don't have the disease. So you have someone who he has some mild symptoms of corona, for example, and he wants to take the test, for example. He is negative, in fact, in reality, but he was false positive. He was classified as positive. We call it false positive. So this one, no harm from, no problem from this one. So type 1 error, it's okay. It's acceptable, in fact. So people make those tests, for example, and we said no, he is positive, but he was negative. He is originally negative, but we misclassified him as positive. So we call it false positive. So false positive, it's fine, it's okay. False negative, this is the problem, false negative. False negative, we predict no, but he is positive, he is yes. We call it type 2 error. This is very dangerous one. So people, when they try to buy, I mean, people who are working in medical sector, for example, when they buy equipment, they need to check this type 2 error. This is very important. If you are building a system for, hospital or something, you need to check those numbers. If they didn't see those numbers, it will be a problem. Maybe they will not buy your product because they feel that you don't understand, the game and how they, so this type 2 error is very, very important. Prediction error, it's the sum of all false predictions divided by the total number of predictions. This is the error. And in fact, this error, it's 1 minus accuracy. So this one, it's 1 minus accuracy. So prediction error, it's the sum of all positive predictions divided by the total number of predictions. Accuracy, it's the sum of correct or true predictions divided by all total number of predictions. So if you can calculate accuracy, we can calculate error, 1 minus accuracy. If you have error, so the accuracy will be 1 minus error, 1 minus error. True positive rate, we have some equations for true positive rate and the false positive rate, precision, recall. So you need to just go through those, terms. And we have here an example. You have binary classifier for medical testing to determine if a patient has certain disease or not. You can imagine it's corona, for example, or it's a tumor diagnosis. So there are two possible cases, it's yes and no, or positive and negative. So this one, it's positive, and this one, it's negative. We have in total 165 patients, right? We have 165 patients. So this is actual, no and yes, negative, positive. So in fact, we have 5 negative classified as 5 as negative. So this one, it's a true negative. This one, it's a true negative, correct? So you have 50. In total, we have 60, in fact. In total, we have 60 no and 60 negative and 105 positive. So this is actual cases. So in fact, we have 60 negative, 105 positive. From those 60, we have 50 has been classified as no. So this is true negative. And 10 they are negative, but they are misclassified as positive. So we call false positive. So we call it false positive because they are negative. They are negative, but they are classified as positive. So it's false positive, or we can say that this is type 1 error. Right, type 1 error. On the other side, we have 105 positive. 100 of them has been classified as positive. So this one true positive. Right? What is remaining from those 105? We have 5 here. Those 5 are positive, but they are misclassified as negative. So we can call it's false negative. Right? So false negative, it's a problem, false negative, because he is positive, but we told them, no, you are negative. He has corona, but we said, no, you don't have corona. So this one will be type 2 error. Type 2 error. So, so the model has 60 negative, and our model was able to classify 55 of those, right? And we have 105 positive, and the model was predicting 110 as positive, right? So this is the predicted, this is actual. Predicted positive, this is actual positive. Predicted negative, this is actual negative. So just, I mean, from those we can find the accuracy. So the accuracy will be total positive, true positive plus true negative divided by total. This is the accuracy. What is the true positive? So the true positive, this is the true positive and the true negative. So this one true positive, this one true negative divided by total. So it will be 150 divided by 155. If the accuracy is 91%, so the misclassification rate or error, prediction error, it will be 9%. Right? We call it error rate. What is true positive rate? True positive rate when it's actually positive. How often does it predict? Yes. True positive rate, it will be 110. This one, true positive rate 100 divided by the actual 105. Right? This is the true positive rate. So true positive rate, in fact, it will be total positive. It's a true positive divided by actual positive. So it will be 100 divided by 105. This is true positive rate. False positive rate, it will be 10 divided by 60. This is false positive rate. True negative rate, it will be 50 divided by 60, right? So we can get lots of numbers from the, confusion matrix, but confusion matrix is very, very important. And when you are building a model, if it is for classification, it's expected that people need to see the confusion matrix, because from those confusion matrix, you can find which cases are usually are, the model can confused with, maybe we have two classes where the model are confused. So maybe we can take those out from the data set and build a separate model for those, for example. We have precision, and the precision, it predicts, yes, how often it is correct. It will be 100. It's like true positive rate, in fact. Precision, it's how many positive predicted compared to the total predicted positive. So it will be 100 divided by 110, and so on. So anyway, confusion matrix for iris. You have been working, Muhammad Saad, for example, he has been doing perceptron and logistic regression for iris dataset, and he has very good accuracy. So can you do, can you calculate the confusion matrix? Can you calculate the confusion matrix for your models? Yes. We have very nice command, in fact. Yes, okay. So I will just let you try first. So So please try to so we have very simple command here. It's called the confusion matrix. Just confusion matrix. And the input to this confusion matrix, it will be the true labels and predicted labels. We will have y and y predicted. So the input to the confusion matrix here will be y and y predicted. True labels and the predicted labels. For this binary classification problem, we have two classes. We just selected the first 100 points. The first 100 points corresponds to the first two classes, which is Setosa and Versicolor. So we have 50 class 0 and 50 class 1. I think we have here, maybe we selected 99, not 100 in fact. Because the accuracy here it's 100%, but we have here 50 class and 49 class. So maybe y and y predict, we didn't use the exact number, maybe. And if you want to plot it, you just need to run this code here. So you need to plot matrix show or match show your confusion matrix, and after that you just need to write text inside. We will have introduction to multi-layer neural network. So should we go for it or? Okay, for the perceptron, it's 3 classes. Yes, very good, Muhammad. So he can calculate the confusion matrix for the perceptron. And in fact, in the first class, you have so we have here 3 classes. We have 0, 1, and 2, for example. So if we can go back to this one, we have 49. So we have 49 class 0 classified as 0. We have 0 from this class classified as 1. We have 0 from this class classified as 0. We have 50 class 1 classified as 1. So this is how, and all numbers across this diagonal, we try to, this is a true label and this is predicted to maximize numbers across this diagonal. This one, it's type 1 error and type 2 error, we try to minimize as much as possible. So it's very important to, I mean, when you are working with any problem, you need to start with, first you need to load your data points, and after that you need to do some pre-processing, normalizations, standardization, for example, and after that you need to select a model for solving your problem. Your model will have lots of hyperparameters. So which activation function you want to select. If it is straightforward neural network, how many hidden layers, for example, how many units in each hidden layer, and so on. And after training your model, you need to check the performance of your model. So one way for doing it is using confusion matrix. So confusion matrix is a very important tool and people are expecting that when you are working, you are doing some research, you are doing some projects in machine learning, for example, or statistics, you need to, present your confusion matrix of the model, because people will need to check the performance of your model, how it will perform with all different classes. For example, if we are working with MNIST dataset, it's digits from 0 to 9, we will discover that sometimes the model is more confused with digits like 1 and 7, for example, they are closer. Maybe 8 and 9, sometimes they are closer. So there are things which can be fixed, but there are things also which it's hard for the model to differentiate between some cases. So as I mentioned, 1 and 7, maybe 0 and 8, sometimes maybe 8 and 7, sometimes 8 and 9. It has lots of confusion between 8 and 9. So it's really important to plot your confusion matrix, because the confusion matrix also it will give you more details about how your model is performing. Okay. Okay, so we will finish now because we have other group who has a course in computer graphics. I mean the last slide for today, it's single layer neural network. We are using this logistic regression model, and those are the equations which are used for. This is a cost function which we use. So the cost function, in fact, it's a half summation of squared error. This is squared error. It's y minus our target minus outputs. And we try to update the weights in a way to minimize this cost function using gradient descent. So delta omega will be minus eta, which is learning rate multiplied by partial j by partial omega. Finally, it will be this one. If you want to implement it, we implemented it already today. If you want to add some more terms, because this is a cost function, but usually, we will have a problem in maybe overfitting a problem. So we need to modify this cost function in a way to try to resist this overfitting problem and fix it using L1 and L2 regularization techniques. So we will do it later on, but next time we will talk about multi-layer neural network. We will use Keras, for example, because Keras is very easy to use with multi-layer neural network. And next time we will use this example for solving Iris dataset. And also we will try, maybe, this time I didn't talk about error backpropagation algorithm. I don't know if we should go into details or not. It's, we can do it, for example, and maybe we can implement it for a simple feed-forward neural network of 1 hidden layer or 2 hidden layers, for example. But we can do this next time. So from now on, when we are working with any model, at the end, we need to plot the confusion matrix. It's very, very important. So, for example, as you can see here, it's a confusion matrix for Iris dataset. We have some cases where the model is confused. So, for example, this one, what does this one mean? It means, in fact, class, it's three cases or 3 examples from class 1 was classified as 2. So, in this label or class 2, for example, we have in total 30 in total 40 examples or 40 samples. So 37 was correctly classified as 1, but 3 was misclassified as 2. So confusion matrix will help us to understand how the data set, and also how can we fix the problems in our model. Yeah, so about Wednesday. Okay, so I will talk. We have lab part in each Wednesday. So I will talk to Mingtao to make it 2 hours earlier. So instead of we are starting now at 5. So we can start at 3, for example, or at 2. So I will send him an email, and he should create a Zoom link, and add all people, invite all people to those lab sections. And in the lab part, please try to be proactive and try to give him your feedback and try to ask him to do things which you really want help. So if you have some specific questions, if you have a data set which you want to work with, for example, you can ask Mingtao to assist in that part. So thank you very much for today, and we will meet again next Monday. And please, if you have any comment, if you have any feedback, just contact me by email. Thank you very much. You have all code in GitHub. You have also the slides uploaded to Blackboard and GitHub. And please let me know if you have any suggestion or any questions. The lab, we will talk. I will talk to Ming Tao today. I will send him an email so we can start 2 hours earlier, because now we are starting from 5, but maybe 5 is too late for me, some of us. So I will ask him to start at maybe 3 or 2, for example. Thank you very much for today. Thank you very much. So bye-bye. Any question? Is there anyone who has any question, please? Any question? So thank you very much for today, and we will meet again next week. We will continue with feedforward neural network, and we will try also to get more examples, try to work with other points which we didn't cover so far. And please, from now until next week, try to work with the examples, try to upload new data sets and work with it. And if you have any questions, please don't hesitate to contact me. Thank you very much. Bye-bye.